I'm going to speak about Bayesian hypothesis testing in finite population. This is a work that I developed with Luis Gustavo during my master's degree at USP. So I'm going to start. The outline is basically I'm going to make a little introduction about finite population models and the predictivistic approach. And I'll show two cases, the univariate and the multivariate. In the first one, we consider some one-sided hypothesis and simple hypothesis, and in the multivariate case, it's testing the second order occurrence. During the work, I'm gonna make examples considering a scenario of a small majoritarian election, just to exemplify the models, to make it easy to understand. Then some final remarks and the principal references. So the finite populations model, what we need to know to say that we are going to work with a finite population model, we need to know the population size n, unless of course we want to estimate this value. And they are considered either when the population is small or the sampling fraction is large, which means that the sample size is very close to the population size. In these conditions, we expect that the inferences are more precise from the use of superpopulation models, because we have more information. When we add the value of the population size, we are bringing more information to our model, so the inferences are more precise. We also use to consider these populations, finite population, because sometimes, depending on our prior specification for the model, we cannot extend it. For example, I have a neuron with n balls, and the Bernoulli model, we have balls of two colors in this neuron. For some priors that I choose, for the number of black balls, for example, the model cannot be extended to a Bernoulli model. So this is why we consider this finite populations model also. The notation here, we consider the vector of population values x equal x1, xn, where x is the characteristic of interest for the individual e. This characteristic is always a real vector. The assumptions here is that the population value is unknown, it is exchangeable, and the population is closed, which means this: the only randoms on our scenario is for the unknown values of the population values. When we draw from a sample, for example, we draw x1, so we see the real value of the characteristic of interest for x1, and then the only randoms is on x2, x3, xn. And when we observe the real value. We don't have any kind of measurement error, nothing like this. Since we have a finite population, we consider operational parameters, which they are basically just functions of the vector x. For example, the maximum between x1, xn, or the total. These are operational parameters. And the inference here is carried out through the predictivistic perspective. In this perspective, we just make probability statements about observable quantities, which means there is no, for example, a parameter theta that we don't know what theta is. No, here our parameters are always observable. And so the advantage of working with this perspective is that, as I said, the parameters are observable, and you don't have to define the parametric space. It comes as the result of this function of the definition of the parameter. This perspective is also considered a more pure Bayesian approach, since we are only interested in observing, in forecasting or making inference about about observable quantities. So the goals of this work is to make a hypothesis test for the operational parameters under the predictivistic approach and compare these results with the use of Bayesian superpopulation model. Here is just a first attempt to compare these models regarding hypothesis testing. Usually they just compare the found limits for the probabilities, or for 1 point probabilities, not for the result of hypothesis testing. And I will exemplify by a scenario of elections just to make it easy to understand. The first case is the Univariate case, and we want, for example, a researcher wants to know the amount of votes that a candidate may receive in an election. So we consider xi equals 1 if the elector votes for a specified candidate, and 0 otherwise, and you have the population value belongs to the set. So our operational parameter is the population total, or we could work in the same way with the population proportion of votes for this candidate. So now we need to continue to develop the work to find the posterior distribution of this parameter, which is given by this result. So we have our exchangeable vector of population values, x. We define pt, the prior uncertainty about our operational parameter, and given a sample x1, xn, here we don't have, since we are considering the vector exchangeable, doesn't matter which the sample is. We can take the first 10 elements, and we have this posterior distribution for our parameter. On the other hand, if n is large, we consider the superpopulation model, and we will model not the total, but the proportion, which I call pi, of votes that a candidate may receive. And then we consider the well-known beta model, a prior beta for the proportion. Then we assume that we have now an infinite sequence of random variables Bernoulli distributed, and the posterior will again be beta with the updated parameters. Now the interest is knowing if which is the limit of the votes that a candidate will receive. If he will receive more than 50% or 60%, 70% of the votes. So to do this, we will test the one-sided hypothesis. Then we have, for this finite population model with the operational parameter, and the equivalent hypothesis for the superpopulation model considering the parameter pi. And in this, we consider just the procedure based on the probability of the hypothesis. We just calculate the probability of H0, the posterior probability of H0 to compare these models. Here we have the expressions for these probabilities. First, under the finite population model, we consider T0, this value here, equals N2, which means pi 0 equals 0.5. Here is according to our posterior distribution for T, and here is the density of the beta distribution. So then we think, how are we going to compare these probabilities? So we did kind of a simulation study when we consider a population with 100 units and two sample sizes, 20 and 80, to consider like a small sample size and a big one to see how the probabilities behave. So we have the prior distributions I consider uniform in both cases. Here is not 1, is a uniform discrete distribution that set 0, 1, 100, since the population total can take any value since 0 to 100, which is the population size, and a uniform distribution beta 1, 1 on the superpopulation model. And the sampling total, this value, is a sufficient statistic. So we compute the value of these probabilities for each possible value of the sampling total. And so we have these two graphics for n equal 20 and n equal 80. In the first, we see that here the red line is the finite population probabilities, and the black one is the superpopulation probabilities. So when our sample is small, the probabilities, they basically don't have any difference. It's very similar. The bigger difference here is 0.3 or 0.4, something like this. But as we increase the sample size, our difference increases. Here, for example, if you take the sampling total equal to 38, then we have more than 20% of difference between these probabilities here. Also, if you change the value of t0 or π0, for example, if you want to test if the proportion is less or equal to 60% or 70%, we just dislocate. These curves are just dislocated forward. There is no difference in the behavior. Now we consider simple hypotheses in a way that a researcher may want the exact value, or he wants to forecast the exact value of the proportion that a candidate may receive. So again, we have the hypothesis for the finite population model and for the superpopulation model. And now we note that in this case, this is a sharp hypothesis. So we consider the field Bayesian significance test, the FBST, to test this. In here, we have, this is not, this hypothesis here does not have a zero probability. But we also consider the FBST to test this, and it's nice because it behaved well. So the FBST consists basically of two stages. First, we need to define our tangent region, which in the finite population model is a set of all points that have a probability larger than the probability of H0. And the second stage is the calculation of the evidence value, which is given by this expression. In the superpopulation model, then we have an interval for the tangent region, and this probability will be our evidence in favor of H0. Here F is the posterior beta density with updated parameters. Again, we consider the simulation with the same scenarios before, a population of 100 units, the same prior distributions. And again, we have they are very well behaved, let's say. The behavior is almost the same as before. Almost no difference when our sampling is small, and the difference gets very large when we increase it. For example, here we have almost 30–40% of difference between evidence values. We also note in both cases that the finite population curve, let's say, it increases and decreases much faster than in the superpopulation model, which means that when we increase the sampling total by 1 unit, the finite population model is bringing more information for us than the superpopulation one. Also, if we vary the value of π0 and t0, these curves are just dislocated. And if we consider different priors, I didn't put here to not extend very much, then the superpopulation model is also more affected by the prior distributions than the finite populations one. Now we consider the multivariate case. In here we consider the multinomial distribution, which is just the extension of the first case. And we wish to infer about the proportion of votes of n candidates, A1, An. For each electron in the population, we have the m-dimensional vector, xj, that we take this value, a vector of zeros with one position k, if this electron wants to vote for candidate ak. Our operational parameter now is a vector, population totals again, but it's a an n-dimensional vector, where the tk(x) here is the number of votes in the population for candidate k. So again, we need to define the posterior distribution at the predictivistic perspective for the operational parameter tt. So we consider now our vector an exchangeable random vector, take values on the set, and pt the prior uncertainty about our parameter on the set. And so the posterior distribution given a sample will be given by this expression. And we have all the restraints here of the set with positive posterior probability. Again, if n is large, what we usually do is consider the proportions. So now we have the vector pi1 pi n minus 1, and we define pi n as the 1 minus the sum of the others. These are the proportions of each candidate. So we consider the Dirichlet multinomial model. So we have the posterior will be a Dirichlet distribution with updated parameters. And the hypotheses here that we consider are some joint hypotheses. We consider just 3 candidates to simplify the scenario. And in here, first we have this intersection that no candidate will have more than half of the votes, which means there will not be a second run in the elections. In the first run, actually, this means that there will need to occur the second run of elections. And on the other hand, H1 states that at least one of the candidates will have more than half of the votes, so there will not be a second run of elections. And again, we consider the base procedure to test this hypothesis, which means we just calculated these probabilities of this hypothesis. So under the finite population approach, the probability of H0 is given by this expression. And under the superpopulation model is given by this expression. We can calculate this using the marginal distributions of the vector pi. Here we consider the same scenario as before, population of 100 units, and basically uniform distributions as priors. So T has a uniform distribution on the set, and pi will have a Dirichlet 111 as a prior. We can make the surface to see the behavior of the probabilities, but they are not very informative. We cannot compare them very well. So I just selected some values. First, for a small sample size, we have, for example, if the outcome, again, the sampling total here is a sufficient statistic. So if you have this outcome, 90-90, or any permutation of this 299 or 992, we have this probability is 0.53 for the finite population under the finite population model, and 0.48, which is not a big difference, but it can change some hypotheses depending on your cutoff, something like this. And again, when we increase our value, the sample size, we have big differences, bigger than in the first model. Here we have, for example, in this case, for this 37,538, if the sampling total is this, we have a difference of 36%, and here 37% difference between the probabilities, just by changing the model. So some final remarks. In this work we just explored some difference regarding hypothesis testing between finite population and superpopulation models. For small simple fractions, the approach is always yield similar results, but they can be very different when we increase as the simple fraction gets larger. And the fluctuations of the null hypothesis probabilities and evidence, they are smoother on superpopulation models. This happens because in finite populations model, after resampling, in our posterior distribution, the support is very smaller than prior to sampling. So this is why we get more information, and the fluctuations are smoother on the superpopulation models. Some future topics of research is compare another possible operational parameters as the maximum and the minimum. For example, if you consider the discrete uniform distribution 1, 2, theta, and then the curves are not well behaved, as in these cases, it's very strange, the results are very strange. And also finding theoretical bounds for these differences. Find a bound, the difference will be always smaller than a certain value. Here are the principal references, and that's it. Thank you for this.